Testing. Yep, that sounds good.
We have the region.
Go in here. All right. Let's do it. Here we go. All right, welcome. We're going to do some energy and momentum stuff. I'm going to sort of split the talking part into two sections, into momentum and then energy. But we did them as a single unit, and they're mixed together on the repackaged sheet also. So let's start by talking about momentum. And again, we're going to sort of do these same things. We're going to look at some common equations that come up, a few important concepts and pitfalls that you might end up with. And the really important question here of figuring out when to use conservation of momentum. Like, when do you look at a problem and you're like, that's a momentum problem in this case. Okay, so thinking about momentum, the simplest thing, right? We know how to calculate momentum. It's mv. It's important to remember that it is a vector, and it's a vector that is parallel to the velocity. So if your velocity is that way, your momentum is that way. Your velocity is this way, your momentum is that way. They're just scalar multiples of each other, if you like. It is a vector. It's one of the weird ones that doesn't have its own unit. It's not like joules or coulombs or amps or whatever. It's mass times velocity. It's kigams, kilogram meters per second. It's just kilograms times meters per second. Sometimes you can also think of this as being newtons times seconds, which makes some sense. The most important thing to understand in all of momentum is that momentum is conserved in collisions. When two things interact, momentum, the total momentum of the system is constant. That is, if I add up all of the momenta going in and all the momenta coming out, my total momentum stays the same. That said, there is an exception to that. Assuming there's no external forces, that all the forces are just what's going on inside the system. If there are external forces, then you're going to lose some momentum to those. The system is not closed. Yeah. I always do. Yes, I'm recording it right now, and I'm recorded saying that. So basically, most momentum things you can just set up by looking at the MVs going in and the MVs going out. Remember, you do have to take care of positive, negative. A common issue that happens with momentum is like, oh, I've got a velocity going in and a velocity coming out. You got to remember that one of those is negative, and so the change in velocity is actually very, very large. So that's like the number one thing to know about momentum is the conservation of momentum. There's those three kinds of three things to know about those collisions, right? Very common are the inelastic, the sticky collisions. Those are the ones where momentum is conserved. Momentum is always conserved in collisions. Where momentum is conserved, but kinetic energy is not. Kinetic energy is lost. And the classic one, right, is if you think about two objects that have the same mass and the same velocity crashing into each other, if they collide and stick to each other, they're just going to go and not move anywhere. All the kinetic energy gets lost. You can, however, have bouncy or elastic collisions. Those are ones where total momentum and total energy are both conserved. Those are a little bit more complicated, but we're going to try to remember how to do those. And one of the key things to remember about situations in which momentum is conserved is that the center of mass velocity of the system remains constant. If whatever the center of mass is doing, it just keeps doing that thing before the collision, after the collision. The center of mass velocity is nice and constant. They will ask you questions about that sometimes. What if there is an external force? How do we actually change something's momentum? We change momentum through forces, and forces cause what are called impulses. The calculusy way of thinking about this is that force is the rate of change of momentum. It's dp dt, which means if I integrate my force over time, I get a change in momentum, and we call that an impulse. The integral of force with respect to time gives us our impulse. In the event that we have a constant force, rather than having to integrate force, we can just multiply it. We can just do force times time instead of having to integrate. And this leads us to our nice fat equals mav equation, which we can use either if we're thinking about constant forces, or sometimes they'll ask for the average force. Remember, the average force is, what would the force be if I pretended the force were constant the whole time? So fat equals mav is a helpful one. They give you most of these. They don't give you fat equals mav. They kind of expect you to be able to deal with it, but it does come up sometimes. Remember, fat equals mav isn't that strange. If you divide by delta t, you get m delta v over delta t, which is just ma. So it's just another statement of Newton's cycle. A few little side things that come up in momentum are finding the center of mass of a system. So one thing that we do have to remember how to do sometimes is to find the center of mass of the system. You're in luck though, they give you the formula on your formula sheet. So here we've got a system where we've got a bunch of objects. Let's go ahead and let's give them some masses, shall we? We've got 3 objects. What's the mass of object 1? Give me the number. 5 kilograms. There's object 1. Object 2? 2 kilo. Did you both say 2? All right, object 3. Right. And what I'd like to know is I'd like to know where the center of mass of the system is. What I can do is I can add up all of my masses times positions and divide by the total mass. So let's think about where is the x center of mass of this system. In this case, I got to look at all of the objects and their x position. So I'm going to start with M1. It's got a mass of 5 kilograms. What's its x position for M1 down here? 0. It's sitting at the origin, which isn't to say it kind of looks like it doesn't contribute anything. I prefer to think of that as it kind of pulls the center of mass towards 0. Plus 2 kilograms, that one's at an x coordinate of 4. This one is 4 kilograms, and it's at an x coordinate of 3. And in this case, our total mass looks like, oh, conveniently, you've given me 11 kilograms of total mass. Beautiful. If we look at the top here, we're going to get 8 plus 12, or 20 over 11. Which is, of course, just a gorgeous, perfect, beautiful number, which is going to be like 1.81. So the x coordinate of our center of mass is like there. Is about there. 8 plus 12, yeah. Which again is actually a little further to the left than I would have believed, but no, I guess that's okay. There is 6 kilograms over here, but it's kind of spread out a little bit, and like so that's plausible. I think we've done that correctly, right? 3, 4, 8, 12, 11. Yeah, no, that makes sense. Let's go ahead and try to find our y coordinate here. We're going to repeat the same thing, just using y values. So our 2 kilogram mass is also at a y coordinate of 0. But now our 4 kilogram mass is also at a y coordinate of 5. Wow, we did a great job here. This is also 20 over 11. Good job, everybody. We got exactly the same number. So it tells me that the center of mass of our system is right there, which again feels okay to me. Like it's not perfect, but it feels all right. What if I wanted to find the center of mass velocity? Well, in that case, what I could do is I could think about taking derivatives. And what you're going to find if you take your derivative, right? Let's say the x velocity of your center of mass. What you're going to find is that when you take the derivative up here, your masses stay. But what you're going to be looking at are the masses times the velocities, or if you like, the total x momentum over the total mass. So this hopefully also make a little more sense why the center of mass velocity is constant. Because if our total momentum is constant, then the center of mass velocity never changes. Looking through this real quick, let's see if we can work this out. That's going to be, oh wait, oh, these are forces. That's really weird. I'm not going to worry too much about the center of mass velocity. Do you want to do it anyway? It stays constant. It stays constant. Yeah. This would be pretty unusual for them to give you something like this. Yeah.
What if it's like objects?
Yeah, so if it's like objects, right? And we actually looked at some of these before, right? So like if you remember, we did that whole lab, right? Where like, oh, I got a thing, right? I want to find the center of mass of the thing. Carve it up into like squares or rectangles, right? And you can, if they don't tell you the mass, you can sort of do it by area, right? Assuming it's constant density. And then kind of think of sort of having three objects that are the center of mass of each of the things. They have done this before with like wires or like shapes like this. Often on multiple choice questions, you can often eliminate a few of them for being unreasonable and then work your way through the math for the other ones. But we did this for the lamina, and like, if you remember kind of the feel of that a little bit. There was one other thing that I wanted to talk about, which is how to solve elastic collisions. And I feel like I forgot to make a slide for that. So inelastic collisions are really easy. They stick together, the masses combine, right? Those are inelastic or very straightforward. Elastic collisions tend to be a little bit more difficult, but we developed this method to deal with them. And so we're going to make up a little collision here. All right, we got two boxes. How big is this first box? We're going to use some symbols here.
X.
All right, we'll call, or M. We'll give it a mass of M.
Oh, yeah.
All right. Is it moving? Yeah, it's moving. How fast is it moving? V. All right. It's going to hit another box. What should the size of the other box be? 2M. We'll make it 2M. All right. Is this one moving? No, we want it to stay still. Okay.
Or should we have it after?
Let's. How about this? Ready? All right. There we go. So that little one's going to catch up to the big one and rear end it. All right. So the way that we did elastic collisions is the first thing we tried to find the center of mass velocity of the system. And the way that we did that is, again, we looked at the total momentum over the total mass. So let's go ahead and look at the total momentum of the system. What is the total momentum of our system? Yep, it's going to be 4 mv. And the total mass of our system is 3m. All right, so the center of mass velocity of our system is 4/3 v. And so if you recall, what we did is we shifted into the center of mass frame. And the way that we shifted into the center of mass frame is we imagined ourselves moving at 4/3 v this way. So we're now moving 4/3 v to the right. Little m is still moving faster than us, right? But not a lot faster than us. So what are we going to do to its velocity? Subtract. We're going to sort of imagine, so we're going to subtract it. So 2v minus 4v over 4/3 is going to give us 2 minus 4/3? 2/3, right. So this one now looks like it's moving 2/3 v this way. We're actually going faster than the big box. It's going to look like it's going backwards a little bit, right? And in fact, we're gonna, if we subtract this one, it's gonna look like it's going negative 1/3 v. So what we've done is we've basically shifted all the velocities 4/3 v that way. Because we're going 4/3 v this way. Everything else looks like it's a little slower. One thing to note, if you've done this properly, look what our total momentum looks like now. 2/3 MV, negative 2/3 MV. In the center of mass frame, the total momentum looks like nothing, because you're following that center of mass. The center of mass of the system looks stationary. And the reason we do this, the advantage of doing it this way, is that when the collision happens in the center of mass frame, the two objects just reflect. What that means is little m is now going negative 2/3 v. This one's going positive 1/3 g. So in the center of mass frame, they just reflect back the way they came with the exact same speed they had. And then what we do is we come out of the center of mass frame. We subtracted, we kind of shifted everything 4/3 v that way to get into the frame, which means to get out of the frame, we're going to shift it 4/3 back the other way. So I had negative 2/3 plus 4/3 gives me 2/3, yeah. So notice this one's slowed down quite a bit. And this one, v/3 plus 4/3 gives us, I got 1/3 plus 4/3. 5/3.
So once they collide, they turn back with the exact same speed, but like the negative,
Yeah, the exact same, they reflect.
they reflect exactly.
Yeah. And so what do we find in the end? Both boxes are actually still going this way.
Oh, okay, so you just put them in terms of each other's.
What do you mean?
Still, 4/3, looking and I'm trying to losing my mind.
Okay.
There's 4/3 to the.
Yeah. Yeah. You're when you shift to the center of mass frame, you're kind of watching this collision happen
Yes,
through a moving frame. And so like, kind of like being in a car,
yeah,
if you're driving this way, this car looks only a little bit faster than you. This one, even though it's going this way, you're passing it. It looks like it's moving backwards to you.
okay,
Yeah.
thank you.
So what do we get out at the end? In the end, both boxes are still going that way, but this one has slowed down a bunch and has boop, bumped the 2m forward. You can in fact double check this. Like again, we started off with a total of 4 MV worth of momentum. We should still have 4 MV worth of momentum, right? The momentum should be the same. We've got 2/3 MV plus, this one's gonna be 10/3 MV, which is 12/3. So our total momentum is still conserved. And if you were to go through and check the total kinetic energy before and after, you would also find that they're the same.
So at the end, you add back.
Right.
The center of that.
Yeah, the way that I like to think of this is you shift to the left. And then to get into the frame, you shift back to the right. Of course, depending on which way the initial momentum is going.
I kind of some of this, so I think in the beginning you have like, there's a velocity zone, but can you just like kind of go through the process again, like how do you?
Okay, so the first thing we do is we have to find the center of mass velocity, because there's a center of mass of this system somewhere. And that center of mass is itself moving. And so what we did is to find the center of mass velocity, you're looking at the total momentum divided by the total mass. And if we look at the total momentum of our system, it's 4 MV. We got 2 MV and 2 MV, but our total mass is 3m. So the center of mass of the system is moving 4/3 v. It's moving a little bit faster than the big box, but slower than the small box. And so what we do is we're going to move into what's called the center of mass frame. We're going to move into a frame where we're moving along with the center of mass. We're going to kind of watch this collision happen from a moving point of view. And the advantage of doing that is that in the center of mass frame, the two objects just bounce off of each other. You know, you can figure out their final velocities very easily. But in order to get into that frame, we're moving 4/3 to v to the right. We're gonna shift all the velocity of the system 4/3 to the left. Because again, if you're driving in a car, right? And there's another car next to you. You could be going 60 miles an hour. If it's going 62 miles an hour, you only see it going slow relative to you, right?
Oh,
The relative velocity is 62 minus 60 is only 2 miles an hour.
but.
So the little box is moving a little bit faster than we are, but not a lot, right? And we're going faster than the big box, which means we're gonna catch up to it and we're gonna see it go to us, it's going the other way, right? It's going backwards relative to us. Okay, if you're going, here's two cars. This one's going 60 miles an hour. This one's going 30, right? If you're going 40 miles an hour, from your perspective, how fast is this car going? 20. This one's going backwards relative to you. You're passing it, right? So we are going, this one looks a little slower. This one actually looks like it's going backwards. Yeah, so we're shifting, we're subtracting that 4/3 v from everybody's speed to get into the center of mass frame.
Okay,
We're then gonna flip it and go back and flip it, and then we're gonna add the 4/3 back. So, this doesn't come up that often. Honestly, full elastic collisions are fairly rare, but they come up from time to time.
and just sure, so when we're doing this whole getting into the room and getting back out, we do it to get, with, like, I don't know, what are we getting at?
We're getting the final state of the system after they collide.
Oh, like the reshoots.
Not just, we're actually getting, like, these two boxes bump into each other and we know what's happening to them afterwards. Because they're not sticking together, this is a fully elastic collision where we're conserving all of momentum and kinetic energy. So like, we know the full state of the system after the collision. How do you know when to do momentum things? The most important thing with momentum, any kind of collision. I cannot tell you how many times people have had a problem on the AP exam where like two boxes bump into each other and they want to use conservation of energy. No, bad. The moment two things collide, they stick together, they're hitting each other. The first tool you should reach for in your toolbox is conservation of momentum. So like, here's an FRQ, right? An old FRQ where they like launch a thing, they launch a little dart and it hits a box. The launching of the dart, up until the moment it hits the box, that's projectile motion, that's kinematics. The moment it hits the box, that's conservation of momentum. Because that collision is going to happen and it's going to start to swing with some speed. If you want to know how fast it's going after that collision, you have to use momentum. If you try to use energy, you will get the wrong answer. Because inelastic collisions where things stick together lose kinetic energy. Kinetic energy is not conserved. Yeah.
Wait, doesn't it become an energy bomb right after though?
Okay, right after that, then it swings up to stop and then it becomes, so this is like a kinematics into momentum into energy kind of question. Similarly, here's one where they had a box hitting another box and that other box is attached to a spring. That box is going to come in, they're going to collide and stick together. And it's going to be a momentum problem for just a moment, right? They're going to collide. How fast is the system moving after they collide? Then it's going to start to compress the spring, and that's an energy question. But to figure out how fast it's going when it starts to compress the spring, you got to do momentum for the collision. So like the moment things collide, you have to do momentum. Sometimes you'll also encounter situations like this, where you've got like a guy on like a frictionless disc. You can do a little conservation of momentum because if he throws a ball to the right, he's going to go the other way, right? What's that? Yeah, it's kind of like an inelastic collision. There's no momentum at first, so whatever momentum the ball gets, the rest of the system is going to get in the other direction. Right? Your total momentum started at 0, so your total momentum has to end at 0 also. Yeah. Okay. That's the number one thing. Any kind of collision, the moment this like they collide, they stick together, you should reach for momentum right away. Other kinds of questions are ones that involve mass, velocity, time, and forces. If it sort of looks like a kinematics question, but then they've also thrown mass in there or they've thrown forces in there, it's possible that you're going to want to do some momentum to it. Time really being the big one there. Certainly if they ask about impulse, or momentum, that's kind of a dead giveaway. And then force versus time graphs. If you get a graph that's got like force versus time on it, that's impulse, that's momentum, right? You want to take the area under that graph, most likely. All right, momentum. We're going to just go ahead and talk about energy now because the multiple choice questions are all mixed up. Yeah, so let's go ahead and talk about energy. Working energy. Yeah. All right. And I put these together for a reason, even though they're technically separate units, because they bear a lot of similarities. So energy has one main difference from momentum, which is that energy is not a vector, it's a scalar. It's just a number. You don't have energy in a particular direction. It's not up or down or left or right. It's just a number. It's measured in joules. Energy is always conserved, but unlike momentum, it's not always conserved in like a useful way. If two things collide, momentum is literally like always, always, always conserved. The problem with energy is that usually if it's just kinetic and potential, it's perfectly conserved, a pendulum or something on a spring. But when you get friction involved, you can end up with energy that is technically conserved. That energy has gone somewhere, but it's no longer in the system in the way that you think it is. So it is always conserved, but you do have to be a little careful. Forces can also change your energy. They do work. The important thing to remember about work is that your force and your displacement have to be parallel. If your force is constant, you can just multiply them. If your force is not constant, you have to do an integral. Now it's written this way on your formula sheet well, for those of you in multi, it's written as a line integral because it's a line integral. That dot product makes sure that they're in the same direction. But for the most part, we can get away with thinking about if your force is not constant, of just doing integrating the force dx, or with respect to whatever variable. Force changes energy over distance. This is sort of a mirror to impulse, right? Impulse is the integral of force with respect to time. Work is the integral of force with respect to distance. So keeping those separate is always good. They give you a lot of beautiful equations for energy, which is really, really, really nice. Don't forget power. They give you two equations for power and you can use them both. That's really, really good. There are a couple common equations that are not on your sheet. One, which is sort of a kinematics one, is that if you like drop something, if you just take an object and drop it, it arrives at the bottom with the speed √2gh. This is only if you drop it from rest, right? If it's got some velocity when you start, it's a little bit more complicated than that. But that's a really handy one to have in your pocket, right? They're like, oh, a ball falls a distance h onto a thing, and you're like, boom, √2gh, I got the speed. One that I want to remind you of, which you probably used once or twice on a UT Quest and then forgot about, is any kind of pendulum. If they're like, I pull a pendulum up and then let it go, how fast is it going at the bottom? You need to find that delta H. You need to find that height. And the height you can do a little bit of trig, is L times 1 minus cosine theta. You can also write it as L minus L cosine theta. That's the height. If I pick it up just a little bit and drop it, that's the little bit of height that it loses rolling back down. So those are some common ones.
Oh, wait, think about it.
Those are some common ones.
You said all minus cosine theta is the distance for that.
Yeah, that's the height, right? So if I have like an object here and I pull it back a distance theta and I let it go, it's not going to fall that far, right? It's only got a little bit of a swing down. That's gonna give you that distance down there that falls. Where L is like the length of the string. One thing that comes up sometimes, and we had this on the exam that we took, are potential energy graphs. It's one of those little pocket topics that will definitely come up from time to time. The most important equation for those potential energy graphs to remember is that your force is the negative derivative of your potential energy function. No, that's like one of the more important ones that's not on your formula sheet. It's one of the more important ones that's not on your formula sheet. The advantage of this is that you can sort of look at your potential energy graph and think about it almost like a roller coaster. If I put an object at position x2, I can imagine it being like on this graph. And if I like put a thing on this graph and I let it go, it's gonna fall, right?
Sorry for the interruption. If Maria Dominguez can come to the main office, please. Maria Dominguez, thank you.
It's gonna fall. Now, the important thing to realize is that the actual object is not necessarily falling. What's happening is it's gonna get pushed towards x3. It's gonna be losing energy, but it's gonna be pushed towards the right. It's gonna pick up a bunch of speed, and then it's gonna go back up that hill and slow down. The graph is just a visualization of the energy that it would have at different points. One way to interpret these graphs is to draw a line representing the maximum total energy. So let's say I have, I'm gonna go to x3, right? And if I'm at x3, if I'm here at x3, right, I have no potential energy. So let's say I give that object 1 joule of total energy. What you can do is you can draw a line right here at 1 joule. Now, if I've got no potential energy and I've got 1 joule of total energy, where's that 1 joule? What kind of energy is that 1 joule? Probably kinetic, right? I've got 1 joule of kinetic energy. Now, I don't necessarily know which way this object is moving, but the idea is, let's just say it's moving this way. If I have 1 joule of kinetic energy, it's going to have some energy to move, right? But as it goes up this curve, that means it's gaining potential energy. And if it's gaining potential energy, it's losing kinetic energy. Where is it going to stop moving? Yeah, where the total energy and the potential energy cross. Why there? Well, if all of my energy is potential energy, then I don't have any kinetic left, right? So my object's going to go up, it's going to stop, and then it's going to fall back down, and then it's going to stop, and it'll just keep bouncing back and forth. How could I get it out of this hole? I have to pump more kinetic energy into it, right? In order to get it out of this hole, I need to pump it up to, like, if I give it 3 joules of kinetic energy, right? If I give it 3 joules of kinetic energy, it can't make it up this hill, right? It'll stop. But it could make it to the top of this hill, right? And if I give it a little bit more than 3 joules, it could even get over that hill into the next little bit.
So when it comes back, we'll just like go over it.
Yeah, it'll go. Whoop. Yep, absolutely. Yep.
So why is force the negative?
So the reason the force is the negative derivative is, imagine that I put my object here, right? It's going to feel a force pushing it to the right. Yeah. It's a little weird. Remember the graph, it's very tempting to think of it being pulled this way, but this is, or down. This is a potential energy as a function of x. So I want you to think about like your object moving on like a road, right? It's getting pushed and pulled by some force you can't see. And all you know is at any given position along the road, how much potential energy it has, right? So at this point, it's got some potential energy, right? But if it's at this point, if we kind of think about our graph, it's going to want to move to higher and higher x values, right? Which means it's going to get pushed that way, right? If it's getting pushed that way, that's in the positive x direction, right? What's our slope there? our slope is negative. A negative slope gives you a positive force. Over here, my slope is suddenly positive, and as my object enters that region, it's gonna get pushed. It wants to get pushed in the other direction. At places where my potential energy is constant, I get no force. It's happy to roll along, just happily. This is a little bit similar actually to our electric field. Remember how electric fields are the negative derivative of voltage? Things generally in our universe want to go to lower energy, right? And so if there's a place that has lower energy than another place, you're gonna feel a force pushing you in that direction. So when you're over here, it's like, hey, if you move to the right, if you go to x3, you're gonna be at a lower energy, you should go that way. But if you like overshoot and you're over here, it's like, no, go back, go back. Yeah.
Oh, it's pushing to negative x value when you're at a positive.
When you're at a positive slope, it's pushing you backwards. When you're at a negative slope, it's pushing you forward. Yeah. So that comes up from time to time. This is the one you got to remember. We had a question on the exam, I remember, where it was like, and now sketch a, here's the potential energy graph, sketch the force graph. And it's really just like a BC calculus question of like, sketch the negative derivative of the thing. All right. With that in mind, how do we know when it's energy? One of the key things is energy usually doesn't involve time, unless it's a power question. That does happen from time to time. But a lot of times, energy relates velocity and position. And the best way to know that it's an energy question is like, things that would be really horrible or inconvenient to do another way. Oh, I'm gonna roll this ball down a hill, and I wanna know how fast it's going at the top of this loop. I don't wanna do kinematics. I don't know like which way the acceleration is, and like, I don't wanna have to figure out the exact curve of this thing. I just wanna be like, well, it's got potential energy here and it's got kinetic energy there, like done, right? So a lot of these very inconvenient scenarios, energy is going to be your key to unlocking them. And in fact, energy is very, very common. If it involves springs or pendulums, great. It's often an energy question. Certainly if they give you a force versus position graph or a potential energy graph, that's going to be a big giveaway, right? If I have a graph of F versus X, that graph's going to tell me about my work. So here we've got one that's going to be a little energy question to figure out like how fast it's going at the top of the loop. Then it turns into like a forces question of like centripetal forces and normal forces and how fast does it have to be going to like make it through the loop without falling. Here's one that was given a number of years ago where they just straight up give you a potential energy function. And then they're like, and go. That's certainly a potential energy graph. Here we've got a very excellent energy question where we've got a box that's gonna like slide down a ramp. So it's gonna get to the bottom going root 2GH. And then it's gonna like hit a spring and compress the spring. So all of the initial potential energy turns into kinetic and then turns into spring potential. The biggest skill with energy is just writing those conservation of energy equations. If you remember from the practice exams, there were a lot of like, okay, I start off with like 1/2 mv squared, and then it turns into like 1/2 kx squared, but then also there's like some energy that was like lost to friction or whatever. Just really make sure you're like, where is all my energy before? Where's all my energy after? And if you can write out that equation carefully, it's going to guide you to where you need to go. All right, let's do some things. So I'm going to pause this and we're going to take some time to work on some questions from the packet.